Welcome everyone to the third video of the 3 video series of equation of motion case number 3. So I will just recap for about what we have learned. So till now the question which was given to us, that in this question we have a 2-cup arrangement in which the outer cup is made to rotate with a constant angular velocity. The rotating viscous liquid also causes the suspended bob which is inside to turn until the torque produced by the momentum transfer in the fluid equals to the product of the torsion constant Kt and angular displacement theta b of the bob. So in the video number 2 we use Navier-Stokes equation to find the V theta of equation. The V theta that we found by solving the equation is equal to V theta we found is equal to omega naught r into r small r by kappa r minus kappa r by small r divided by 1 minus kappa minus kappa. So this is the value of V theta which we found. So in this question we have to find torque exerted by flowing fluid by suspended block. So what will be the torque? Torque will be basically drag force into movement arm. So what will be the value of drag force? Drag force will be just equal to momentum flux by flowing liquid by suspended block. So that will be basically our drag force. So how will we find the momentum flux? We will just multiply stress into area to find it. So how we can obtain stress? We will just use Newton's law of viscosity. Law of viscosity to find the stress. From stress we will find momentum flux, which is basically drag force, and we will multiply by momentum arm to finally find the torque exerted by the flowing liquid by suspended block. So let's proceed. So what is Newton's law of viscosity? The expanded form of it is minus mu into del V plus del V transpose plus 2 by 3 mu minus K into del V into delta. So this is finally the value of tau. The value of del operator is delta r plus tau by dou r plus delta theta dou by dou theta divided by r plus delta z dou by dou z. So this is the finally value of del. The value of del V, we know this value is going to be 0. The second part. Now the value of del V is basically summation of I summation of j delta I delta j d dou xi vj. This is with really complex calculation. For transpose the value is dou ij delta I delta j dou xj and vi, just opposite of del V. Now the value of shear stress of R at theta component is minus mu by Vr d by dr into V theta by R, obtained from Newton's law of viscosity. Now we know the value of V theta was mu naught R into R by kappa r minus kappa r by small r divided by 1 minus kappa minus kappa. So we will just put the value of v theta into this equation. By putting this value, we will find theta is equal to minus mu r d by dr, value of v theta, which is v theta into r to r by kappa r minus kappa r by minus kappa r, this capital, this small r, 1 minus kappa minus kappa. Before, and we have to divide v theta by r, so small r will come here. So dividing by r, we will get this will be 0 and this will be r square. Now we will differentiate this equation which we have found. By differentiating this equation, we will get minus 2 mu omega naught into r by r square into kappa square 1 minus kappa square. So this is the equation we have found. The equation is shear stress exerted by the moving fluid on suspended board, but we have to find it at r is equal to kappa r. The shear stress, this is the equation which we have found, is basically the shear stress exerted by moving fluid on suspended board. So, but we have to put the r value to find at that exact location. So by putting r is equal to kappa r in this equation, value of r is equal to kappa r, we will get tau r theta is equal to minus 2 mu omega naught 1 by k square kappa square minus 1 by kappa square. So basically this is the value we found, and minus tau r theta at r is equal to kappa r will be basically 2 mu omega naught 1 minus kappa to kappa square 1 minus kappa square. So we have basically found the shear stress exerted by moving fluid on the suspended board. So this is basically shear stress by moving liquid on suspended board. So in this diagram, when this fluid moves, so it is basically the shear stress by moving liquid. Liquid is between these two curves on the suspended board. So what we have found is basically shear stress by moving liquid on suspended board. Now moving on to the next step. Earlier by discussion, we know that by multiplying by area, we will get momentum flux, which is basically the drag force. And to find the tau, we need to find the drag force, and drag force is basically momentum flux. And to find momentum flux, we will multiply this quantity into area. So multiplying this quantity by area, we will get minus tau r theta into 2 pi k r l. This is basically the area, which is nothing but drag force by moving fluid on that suspended board. Now to find the torque, what is torque? Torque is basically drag force into moment arm. So to find the drag force into moment arm, we will multiply it by the radius. So what is the radius in this case? Is just basically kappa r. So to find the torque, we will multiply drag force into momentum, and we know that drag force is equal to momentum flux. We know that drag force is equal to momentum flux, which we have found by multiplying stress into area. So this is stress and this is area. Now we have found the momentum flux, which is just drag force. Now multiplying drag force into momentum, we will get the torque, which we have required in question. So let's start. We know the value of tau r theta minus tau r theta to r into kappa r into stress into area 2 pi kappa r L into kappa r. So this is basically stress into area into momentum. So this we have found the torque. So by multiplying this 2 pi omega naught 1 by kappa square 1 minus kappa square. So multiplying this into 2 pi kappa r L into kappa r, what we get? We get basically this. The torque we get is 4 pi mu omega naught r square L into kappa square into 1 minus kappa square by multiplying stress into area into momentum. And in question, what was given to us, if you can remember, that the tau Tz, which is basically torque, was given as the multiplication of kt into displacement theta b. That in question it was given that kt is the torsion constant and theta b is the angular displacement. Now this is also torque. Now this is also torque exerted by moving fluid on suspended board, and this is also torque exerted by moving fluid on suspended board. So these are basically the similar values. This was given in the question and this we have derived till now. Now let's say this is equation 2 and equation 1 and this is equation 2. Now we will just equate both the equations. Now by equating both the equation, we will find that kt theta b is equal to 4 pi mu theta r square L into kappa square 1 minus kappa square. Now we have found in question what was given, what was asked, to find the expression of viscosity. And now by rearranging this equation, we will get mu is equal to kt into theta b divided by 4 pi omega naught r square L into kappa square 1 minus kappa square. So this is our final answer which we have obtained from equation of motion case number 3. I will just summarize the answer in 1 minute what we have done. First, we have used the Navier-Stokes equation of theta component and integrated it by using the boundary condition. After integrating, we found the value of theta t, and the value of theta t v theta is equal to this. After that, we knew that that torque which we have to find is equal to drag force into momentum. Now drag force is nothing but momentum flux. Momentum flux is nothing but stress into area. So stress into area, we will find momentum flux which is equal to drag force. Now we found the stress by using Newton's laws of viscosity. After using that, we got momentum flux which is basically drag force, and we multiplied it by momentum to find the torque. And in question it was given that kt into theta b is nothing but the torque exerted by moving fluid on the suspended board. By equating these two, we finally found the expression of viscosity which was basically asked in this question. So thank you. Now Mosh Kumar will explain the applications of Navier-Stokes equation.
There are so many applications of Navier-Stokes equation, like aerospace engineering. In aerospace, Navier-Stokes equations are crucial for aerodynamics and propulsion systems. In aerodynamics, predicting lift, drag, and other forces on aircraft wings and bodies. And on propulsion system, analyzing the flow of air and fuel mixtures in jet engines. The next example is civil and environmental engineering. Okay. The first example of civil and environmental engineering is hydrodynamics, studying fluid flow in rivers, lakes, and oceans. And other is environmental fluid dynamics, modeling air and water pollution discussion. Another third example of Navier-Stokes equation is mechanical engineering, internal flows, analyzing flow through pipes, valves, and ducts. The second one is turbo machinery, designing turbines, compressor, and pumps. The fourth example is biomedical engineering, like blood flow and respiratory systems. In blood flow, modeling blood circulation in arteries and veins. Okay. Our last example is chemical engineering, process engineering. Design reactors, separators, and mixers involving blood flow. The second one is multi-phase flows, studying flows with different phases like liquid gas systems. Thanks so much.
Alright, Mooks, that brings us to the conclusion of our 3 series episode, where we tackled a very elegant yet powerful problem involving the Navier-Stokes equation.
Yes, Om, even thought it was just one problem. It really packed a punch. We explored a classic system, a Newtonian fluid sandwich between two cylinders, where the outer cylinder is rotated at a constant angular velocity, and the resulting flows causes a suspended bob to twist. It's like watching viscosity in action, right?
Exactly. What made it fascinating is how the entire dynamic comes down to a steady laminar tangential flow, a classic case for cylindrical coordinates. And what ties this to the Navier-Stokes is the balance between viscous torque and restoring torque from the torsion wire.
Yeah, the problem is deceptively simple. No turbulences, no pressure gradients, no axial flow. Just a clean rotational case. But it still reveals so much about the momentum. It's transferred in a viscous flood.
And it's also a great reminder that not all fluid dynamic problems need to be turbulent or chaotic to be meaningful. Sometimes it's this clean, well controlled experiments like the rotating cylinder setup that helps us deeply understand the fundamentals.
For sure, and what I really appreciate is how this problem gives us a practical method to measure viscosity. You don't need fancy electronics, just rotation motion, a torsion wire, and a mirror to reflect a beam, right?
Right, that's purely mechanical ingenuity. And by setting up the equilibrium between viscous torque and torsional resistance, we derived an expression for viscosity that actually comes from Navier-Stokes. Simplified, yes, but still very real.
Plus, we see how critical assumptions like steady-state laminar flow, Newtonian behavior, and negligible end effects allow the Navier-Stokes equation to be reduced to a manageable form. It's all about isolating the physics that truly matter.
Agreed. So to wrap, to everyone listening, whether you are just starting out in transport phenomena, or deep into your engineering journey. Remember, you don't need to solve the entire mystery of Navier at once. Sometimes one elegant experiment is enough to open the door.
Yeah, that's the beauty of physics. It's not always about quantity of problems, but the quality of understanding you gain from each one.
This is Soham
And this is Mokshaman Bishop.
signing off for
from
the Flow Unlocked.
Okay, चलेगा. Bye.
Bye, thanks.